But I just wanted to say that this is an organisation, the work this organisation does is honourable, necessary, and for the good. And there are few organisations around about which that can so clearly be said. And I was particularly impressed by Charlie's talk this morning, which I thought was absolutely inspirational. So, okay, we're up. So I'm going to begin by just giving you a route map through this talk. At some point you will begin to lose the will to live, and so the route map, the route map will help you keep going until lunchtime or the break or whatever it is. So I'm going to begin by saying something about climate. I'm going to talk about the energy versus GDP relationship. In other words, the relationship between energy consumption and economy. I think it's really important. I'm going to talk about the role of fossil fuels in today's economy, because we are still in today's economy. And I'm going to talk about the Hubbert Curve, which is an additional constraint that we need to think about, the implications of that we need to think about. I'm going to talk about the logistic nature of energy system transitions, which may or may not be something that you've come across, but basically means you can't, like Columbus, just set off and go straight to the new economy. You start off slow, you speed up, and you slow down again. I'm going to talk about scarcity and substitutability, unintended consequences, and risks to a successful transition. And this is actually me being optimistic now. So if it sounds a little bit pessimistic, don't worry too much. Here we go. So I thought I'd go back a few years. This slide starts about 64 million years ago, and is a graph, first of all, of temperature on the left-hand axis, estimates of the temperature difference between now and then. And what you can see, let's see if, oh yes, it works. What you can see is after a short pause, temperatures start to rise. I can explain why over T, reach a maximum and then begin to fall. And this is as CO2 is being absorbed through enhanced erosion after the collision between India and Asia, which took place around 45 million years ago, something of that order. Crash, mountains, rain, erosion. What we then see is temperatures falling, and the onset of glaciation in the southern hemisphere. This is the beginning of the Antarctic ice cap. One of the things that does is to start to reflect incoming solar radiation out. So less sun is staying around in the Earth's climatic system to warm it up. And so we get this lovely dip in temperatures here. By the way, there is actually nowhere you can put your thermometer to measure the temperature 50 million years ago. So this stuff is all by inference, all by using what climatologists refer to as proxies. Actually, any instrument for measuring temperature is a proxy, if you think about it, even a simple mercury in glass thermometer, but we'll leave that for discussion over tea. So we get this dip here caused by the sudden appearance of a reflector at the bottom of the planet. Chug, 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 and then we get the onset of northern hemisphere glaciation, which gives us another reflector, which causes a further decline in temperatures. And then we get this instability, increasingly unstable climate here as we approach the present. Okay, so that's the long view. And there we go. Okay, and then I'm going to move forward to the last 400,000 years or so. And what we can see here is the last few ice ages. Temperature dropping, rising abruptly, dropping, rising abruptly, dropping, rising abruptly, dropping, rising abruptly. The horizontal scale changes here. This last little bit, last panel, is expanded by a couple of orders of magnitude, at least. So just be a little bit careful there, but this bit does indeed appear to have been different from the behaviour here. When we popped out of the last interglacial here, the temperature, or when we reached the last interglacial here, the temperature started falling almost immediately. Here, we seem to have hit a kind of flat bit. I'll come back to that in a moment or two. Okay, the main factor driving the temperature in and out of ice ages appears to be the ice albedo effect. So once ice starts to form, we get more reflection, the temperature falls. What ultimately stops that process is the Milankovitch cycle, which is the wobble about the wobble of the Earth's orbit around the Sun, which means that at certain periods, every 110,000 years or so, the northern hemisphere or the southern hemisphere will get a lot more radiation, particularly in the summer, which melts the surface of the ice in that hemisphere and causes a lot more solar radiation to be absorbed. And that triggers then the rise of temperature, and we pop out of the ice age. Once the ice sheets start to melt, they melt. Once they start to freeze, they freeze. It's an unstable system. It's a bistable system, a little bit like a light switch, but with more consequences. Okay, moving on. I just thought I'd put that in there. So this little downward excursion here is the temperature effect of the Toba eruption. And the Toba eruption is interesting. It would have been interesting at the time because it nearly finished us off. Apparently, there were about 10,000 humans left at the end of the Toba eruption and subsequent very sharp cooling. Okay, so this is almost as cool as the depth of the ice age, and this was a particularly severe ice age. The last ice age was a particularly severe ice age. And then we popped out, and we popped out about 12,000 years ago. Okay, let's make sure I'm going forwards and not backwards. Yeah, okay. So, as I said, the current interglacial appears to be unusual, and a scientist called Ruddiman in 2003 has suggested that in fact we have been tinkering with the climate for about the last probably 7,000 years, at least 5,000 years. And we've been doing this through the development of agriculture and also through land clearing, which hunter-gatherers do as part of their management of the landscape to facilitate hunting and gathering. So climate change, well, actually what we've managed to do here over these last few thousand years is climate stabilization. We didn't know we were doing it, but we seem to have pulled the trick off anyway, which is really interesting. Okay, moving on. What we've got here is a picture of two things. We've got world primary energy, which I've shown in blue for no particularly good reason, except that I needed to be able to tell the difference between the colours. So there we go. That I think is the reason for that. And then we've got world population here. And what you can see is that they've both gone to the moon more or less simultaneously. Okay, and when something like that happens, you look for a causal relationship between the two. And I assert that the increase in energy consumption has driven that rise in population. And it's driven it as a result of the economic impacts of the increased energy use. There's a whole lot more to say about this. The history of the Industrial Revolution is something that absolutely fascinates me, and I can if anybody is interested, we can talk about that for the rest of the day. Absolutely fascinating. The other thing I wanted to say about this is this, as it stands, doesn't look as if it can continue, as if it can continue. When something like this happens, normally you either get a stabilization, or you get an overshoot and collapse, or you get something in between. Okay, and it will be interesting to see which of those paths the human. Well, it will be. It will be. Won't it? I mean, it's, you know, it's, if you wanted to be born into some dull kind of century or millennium, this one wasn't it. Okay, I was born in the last millennium. That was quite exciting, actually. The last millennium had its moments, didn't it? It had its moments. But on the optimistic side, what I wanted to say is that there are signs that in the last few decades, the rise in population has begun to stabilise. And it's indeed possible, people project that population may peak sometime in the middle of the century, this century. I think that's a really interesting thing that is beginning to happen. All sorts of factors contribute to that, apparently. It's things like the education of women, the fact that people can now have reasonable certainty that the children that they do have will survive to adulthood. And that was not the case for much of the world in previous centuries. So things are changing. Always look on the bright side. Okay. So I talked about the relationship between energy and economy. Energy and economy are correlated. This slide shows the relationship for many countries. Now, a lot of people focus on the fact that, for example, Qatar and Hong Kong have nearly an order of magnitude difference in their energy consumption, but they seem to have roughly the same GDP per capita. So energy consumption is on the vertical axis and GDP per capita is on the horizontal axis. This, by the way, is the way an economist would draw this, where energy consumption is driven by economy. As a physicist, ex-physicist, I would put the thing the other way around and say that economy is driven by energy consumption, but that's just me. So as I look at this, at some stage I'll probably lie down on the ground so that I can see the axes the right way. I apologise in advance for doing that. The spread, the horizontal spread here in GDP per capita for a constant energy consumption, I would suggest is mainly to do with patterns of trade and the subdivision of economic activity between different countries. And that in fact what we should focus on is the average. And if we focus on the average, what we have is a more or less linear relationship between energy consumption, crudely linear relationship between energy consumption and GDP. So energy consumption is really important. The other thing I wanted to say is that much of the energy in this graph is fossil fuel, and the problem that we face in attempting to move to a post-carbon economy is that we may adversely impact the global economy in ways which will have potentially uncontrollable consequences. Okay, so moving on to the next slide. I'm not going to linger on this one, but this is a close-up of part of the vertical takeoff slide that I showed you earlier, and shows the pattern of fossil fuel consumption since 1800. The Industrial Revolution in England started about here, just off the graph, more or less. Historians argue about when. I'm not particularly interested in exactly when. What we have is, up until about 1850, a world dominated by traditional biomass. People burnt wood, dung, plant waste and so on, agricultural waste, to survive. We then have the onset of coal here, grey stuff, oil in blue. The colours The colours are random, clearly. We have gas here, and then we have solar, other renewables, modern biofuels, wind, hydropower, and so on in this top slice. This is more or less where we stand at the moment, globally. And remember that it's the global position that matters. It's not the position on your latest project, or the position in the United Kingdom, or the position in the European Union that matters. By the way, how am I doing for time? Somebody give me a... Halfway through. Okay, great stuff. I'm about halfway through. The other thing on this slide is this, which I think is in about the right place. This was roughly when the discovery of what is still the world's largest oil field was made. This is the Al Ghawar oil field in Saudi Arabia, which I believe contains enough oil to drive the world for a couple of years. I'll have to check that after the session. But it's fairly small compared with what we are now consuming. And of course, this rise is driven by the industrialization of parts of the world outside the industrialized West, places like, most recently, China, India, the Far East. We can see the beginning of industrialization in places like Africa. These are, in many ways, all good things. These are places where people have lived in grinding poverty until pretty recently. And this is now lifting them out. But there are consequences, and we have to face those consequences and deal with them one way or the other. Which one? Let's try that. No, let's try this. Okay. Moving on, there are a number of potential threats to this rosy picture of oil-driven industrial activity, economic activity, which I've been painting over the last few minutes. One of them is this, the Hubbert Curve. This graph has probably generated more controversy amongst economists and energy experts over the last 70 years or something, I can't count, a lot, than any other. One of the things that I think Hubbert first started to produce this sort of stuff in about 1947. Again, I'll have to check. And one of the immediate consequences was that Shell, who employed him at the time, investigated his activities. This is, or was, thought to be a threat to the company that he worked for, the fact that this might happen. We mustn't tell the consumers, because what then? Perhaps we'll end up with nuclear power or wind or something instead. The debate about the Hubbert curve mainly focuses on the fact that Hubbert didn't really predict the peak very accurately. He located the peak around 2000, and in fact, the peak is probably occurring about now, as I will show you next. Okay, what we've got here is Hubbert updated. This is a paper by Lachalère, Hall and Bentley, who have been writing on this subject for a long time. Lachalère, I think, is now in his 90s. He's an old man, but he's still doing interesting work. And what it shows is, first of all, oil production, oil and gas production. These curves here on this side, which refer back to the left-hand axis. And then we have cumulative production on the right-hand axis in gigabarrels. That's not an SI unit, but I'm sure at some stage it will become an honorary SI unit. And what we can see is that the conventional sources have probably already begun to turn over, and people are betting on something like this. And then we have the natural gas liquids, X to liquids, coal to liquids, etc., etc. And also things like fracked oil and gas, making up the difference here. But one of the consequences of the huge rate of growth in the economy that we've seen is that almost anything that you find extra gets gobbled up fairly quickly. okay? It's very hard to keep pace with the growing global economy just by shoveling in extra fossil fuels, extra oil and gas, okay? Another problem that we have is the problem of declining energy return on investment in these things. So as we move to deeper and deeper sources of oil and gas, and in principle coal, we actually saw the same thing happening, by the way, with respect to the UK coal industry from the period from the late 1800s through to the ultimate demise of that industry in the 70s and 80s. So peak UK coal occurred in about 1910. And after that, the direction was only ever downhill. Despite massive efforts to increase coal production, it never happened. Does anybody here remember the plan for coal? 1974, 5, 6, something like that? No? Some of you are old enough to have forgotten the plan for coal, as indeed I do very often. I write it down on pieces of paper and it helps me to remember. Sometimes, I was going to say, one of the things that drives the Hubbert curve is that one finds big things before one finds small things. So one finds the big fields first and produces them, and then one finds the small fields. Sometimes I lose my car, which is quite a big thing. But much more often I lose my keys, which are smaller. And this is one of the phenomena which drives the Hubbert curve, the shape of the Hubbert curve. I hope you all find that helpful. Okay, so what we've got here, this yellow slice at the top, is the energy which is required to produce energy. Now you can see in the past it was unimportant. Yeah. When we were getting oil out of places like Texas and then the Arabia, the Middle East, and so on, oil didn't take much energy to produce, but now the energy input to oil and gas is increasing, and these particular people, Delanoy et al. 2021, predict that by 2050, 50% of the oil and gas that we get out will be used to produce the oil and gas. And that will have profound consequences for the price of oil and therefore for global and national economies. And it's possible that this is pessimistic. It's just possible that ways will be found to produce humongous amounts of oil and gas from very, very deep resources, difficult to get at resources. But then, of course, we have another set of problems, which are the ones that most of you are probably focused on. But all I'm saying is that we are between one problem and another problem, and one of them will get us one way or the other. Okay. Yeah, cheer up, lighten up. Okay, the logistic nature of the technological transition. What we're looking at here is the history of successive energy system transitions. First of all, out of wood, which is shown declining here, to coal, then to oil, then to natural gas, and then to nuclear, which just gets a toehold here. The actual data sticks half an inch up from the bottom of the axis there, and the rest is projection. That didn't, in fact, happen. Not everything that makes it onto the bottom of this axis goes on to displace everything else. And then we have a thing called sulfus here, and these two authors, Marchetti and Nakicenovic, posited that there would be something else that would come along after nuclear and after natural gas. And they didn't know what it was, so they called it solar or fusion, hence sulfus. My colleague and I, Paul Drummond, did a projection a couple of years ago from historical growth rates of wind and solar, hence SolWin, with a nod to Marchetti and Nakicenovic. And If these things grow at anything like the rate that they have been growing and continue to do so over the next few decades, then by about 2050, we will have hit something like 60% displacement, 60% of global energy consumption. There'll still be 40% to go. Something else to say about this is that if solar and wind grow at anything like this rate, they will have grown at something like 3 times the rate of the fastest any of these previous historical transitions. So this will be the most blistering energy system transition that has ever been attempted. Don't try this at home. Okay. Okay. Well, actually, maybe you should try it at home. Okay, moving on. The transition from coal to oil, let's just look at the historical consequences of this. First of all, World War I, then World War II, Gulf War I, Gulf War II, and I would argue also the Ukraine War is addressing difficulties that policymakers, particularly geostrategists, see looming in the future as a result of the last few slides, scarcity, and also the problem of substituting for scarce resources with these new resources. This is going to be a difficult transition, and indeed it's already proving, I think, I would argue, to be a difficult transition. Moving on. Logistic nature of technological transitions close up. What I've done here is to replot these graphs highly schematically. What we see is the growth of renewables here, assuming that things start at 20% per year increase, and we see the decline of fossil. And one of the things that you see here is that the decline is not linear. You don't go straight down, as it were. I want you to imagine that you're on an aeroplane. You approach Gatwick and you head to the runway in a straight line. No, you don't, because that's catastrophic, impossible. Instead, what you do is you descend and then you flatten out, and it looks as though energy system transitions have the same shape. And the maximum rate of transition occurs halfway through, which would take us, starting from now, to about 2050. Again, this is broadly consistent with the previous slide that I showed you. The rate of investment in new technology looks like this. You start off slow, a few wind turbines in Denmark, the Tvindmill. Does anybody remember the Tvindmill? Yes, okay, there we go. I love these conferences. I love the fact that there's always somebody in the conference who knows what I'm talking about. I mean, it's really amazing, really amazing. Rises to a peak about halfway through and then decays. Of course, there are two contradictory phenomena going on here. One is that on the way up we're learning, and on the way down we're tackling harder and harder problems, more and more difficult sectors to displace fossil fuel from. At some point we will have to displace fossil fuel from diesel for earth movers on metal mines, and we will have to replace bitumen from roads. We will have to find a way to make bitumen from plant waste or something at some point. Or we will have to tolerate the fact that we will continue to consume small, perhaps declining amounts of fossil fuels for many, many decades hence. Maybe there are things that we can't. Okay, so this graph is entitled Support from the Old for the New. I hope that makes some kind of sense. I'm not going to explain it. I'll explain it over tea. Prerequisites for I'm almost finished. Prerequisites for a success, thank goodness. Prerequisites for a successful energy system transition. First of all, intact global supply chains. Well, we had those until recently. We're busy trying to dismantle them at the moment. Markets and finance systems, stable currencies, So what we've done over the last few years, and Lifon will say more about this in a few minutes, is that we have printed money like there was no tomorrow. And indeed, it's possible that at some point there will not be. Low interest rates. One of the things that happens when your currency collapses in value is that you try to shore it up by increasing interest rates. That makes it harder to invest in the future. Geopolitical calm. Yeah. Because the politicians are easily distracted. Our politicians, we are easily distracted, but our politicians seem particularly easy to distract. And if there is something else going on, then they will turn their gaze away from the fundamental problems to something more interesting and exciting. And that seems to be what they've done over the last couple of years. Deep reserves of political and social capital and trust. And these are very, very easy to burn through. And I would suggest that one of the tragedies of the last 3 years of the COVID epidemic is that we have burnt trust as if it were a non-renewable fuel. Prerequisites for a successful energy system transition: continued supplies of oil, natural gas, metals, minerals throughout the transition to non-fossil energy sources and beyond, certainly in the case of metals and minerals. Time to work out what works. Your presentation this morning, I forgot your name. Charlie. Charlie's presentation this morning was an absolute masterclass in what it takes to work out what works. His practice have obviously been focusing on that for decades, and it takes time. And to put together a whole new energy system architecture, willingness to adapt strategy and modify timetables in the light of events, a recognition that energy is not the only constraint on global and national economies, and that we have to think hard about other objectives, not just energy, but also things like global development goals and so on. Accepting disagreement as an unavoidable part of strategic decision-making in the presence of multiple constraints and profound uncertainty. Further risks: risk that decarbonisation will adversely impact other economic and development goals, and it's an obvious one. Risk that the transition process will be captured by sectional or industrial interests and used for them and not for us. And increasingly close coupling of subsystems and constraints, generating potentially unmanageable complexity. I'll translate that one into human over tea. References, I'm done. Thank you.